Hey, this is Horner, and this is part 3 of everything you need to know about rotational motion to get a passing score on the AP Physics 1 test. The topic that we're going to talk about now is called torque. It's part of rotational motion, and it deals kind of like force does, although we are going to actually use force in this equation. So we're looking at how force that is working at a radius can affect something like, oh, I don't know, a nut or a bolt if you're trying to tighten or loosen something. So sometimes you'll use a wrench to do that, and the reason we use longer and longer wrenches is we get something called torque, and we get a lot more torque with a longer wrench. So this is the length of the wrench, this is R, and then here's our force, and we can apply that force at many different angles here. If I applied at 0 degrees, I'd just be basically pulling on the wrench, and that wouldn't do anything at all to this nut. If I apply a force at a, whoops, that's really not 90 degrees. If I apply it at 90 degrees from this line of action, then we'd be applying maximum force here, and we would get maximum torque. If we do it at any other angle, we don't apply as much, we don't have as much torque in the end. So the angle here is really important, and we'll want to make sure that we end up using that. So let's go ahead and take a look at a problem. We have a pirate captain takes the helm of a ship and grabs a hold of the wheel. So here's the center of the wheel, and then we know that we have a radius r out to the end of the wheel where he's holding on to these little parts here on the wheel. And he applies a force at an angle of 80 degrees. So here's our 80 degrees, not quite 90, and he does that with a force of 20 newtons. The radius of the wheel here is 0.2 meters, and we know that our force is equal to 20 newtons. So from all that information, we're going to find out what is the torque on the wheels. So we have F times R times the sine of the angle. Our force is 20 newtons. The radius here is 0.2 meters, and then we're going to multiply that times the sine of 80 degrees. When you're done, you end up with 3 point, oops, that's not 3. You end up with 3.94 newtons times a meter. So torque is measured in force times distance, and force is always in newtons, and our distance will always be in meters. So that's the end of that one. The second one, I have a mechanic tightens the lugs on a tire by applying a torque of 110 newton meters at an angle of 90 degrees. The minute you see 90 degrees, you can now ignore the sine of the angle because the sine of 90 is actually 1. They want to know what is the force applied to the wrench if that wrench is 0.4 meters long. So we're going to use our same equation again. Torque is equal to Fr sine of the angle. This time we're solving for force, so force is equal to torque over R times the sine of the angle. Our torque is 110 newtons times a meter, and we're going to divide that by R, which is 0.4, times the sine of 90, and we said that that ends up being 1. If it ends up being 0, then we don't have any torque. So here we definitely want this to end up being something in between 0 and all the way up to and including 1. If you go ahead and do your math here, you should end up with 275 newtons. So that's pretty big force that we're applying to this. For the next one, which is number 17, we'll move this on down. It says, how long must the wrench be if the mechanic is only capable of applying a force of 200 newtons? So now we need to make it a little bit bigger in order to have this so that it will actually turn the things we needed to turn. So we know torque is equal to Fr sine of the angle, and we want the radius to be able to tell us for that torque that we had, what is that radius, since we want a force times the sine of the angle. Our torque, remember in the last one, was 110 newtons times a meter, and we know we can only apply 200 newtons of force this time, so we've got to have a longer wrench in order to apply. Sine of 90 equals 1. So if I divide the two, I end up with a wrench that needs to be at least 0.55 meters long. For number 18, this is more of a ranking type of question, and it says I have a constant force F is applied for 5 seconds at various points in the object below, as shown in the diagram. They want us to rank the magnitude of the torque exerted by the force on the object about the axle located on the center of mass from smallest to largest. So I always want to think about my, my equation, and my equation is torque is equal to F times R times the sine of the angle. So one of the things that I notice is if I try to turn it right at this, I won't get any torque. So this one is essentially 0. And so that's probably going to be the smallest one that we have. So that's going to be B. The next one out away from the center is C, and it's closer to the center than either A or D is. So it must be the next highest amount of torque. Now I've got 2 more, and if I notice, my radius to each one is the same, or my distance to the point is the same. This one is being applied at an angle, and this one is not. This one is right at 90 degrees to this object itself. So if I look right here and right here, that's a 90-degree angle. If I look right here and right here, that's less than 90 degrees. So because this one's less than 90 degrees, the sine of the angle is going to be less than 1. Here it would be 1, and with the same amount of force, A is going to be smaller than D. And so our answer here is BCAD. On the AP test, you would have to explain it, so you could do a lot of what I just did, and just in a written form to kind of let them know what you were doing. The next one here says a variety of masses are attached to different points on a uniform beam attached to a pivot. They want us to rank the angular acceleration of the beam from largest to smallest. So remember, be really, just really simple here. Force is equal to mass times acceleration. So I know that if I can find torque, and remember torque is equal to force, times the radius. If I can find the one that would give me the biggest torque, it's probably going to give me the biggest force and therefore the biggest acceleration. So let's go ahead and take a look at these. The one that is furthest out looks like it's going to be this one. Okay. I also have this one really far out and this one really far out. This one has 2 masses at this distance. So let's do this. This is 1, 2, 3, 4. So I'm going to go ahead and say that force is equal to mass times acceleration. So we'll just call this force. If we ignore the acceleration right here, the force and the mass are about the same. So let's figure out what the torque is, just kind of the proportional torque here for each one. So torque here would be equal to 2 times that 1, 2, 3, 4. 4 times 2 would be 8. This one would be 2 times 3, so our torque here would be 6. This one would be 1, 2, 3 times 2 would be 6, plus, now I've got 4 times 1, which would be 4. So we're going to add up the torques here, and we're going to end up with 10. So the torque is kind of proportional to 10, so yeah, we might put proportions on these. And then on the last one, we've got 1, 2, 3 times 1 would be 3, plus we've got 1, 2, 3, 4 times 2 would be 8. So this one is approximately 11. So looking at these, we can kind of see what the torques are in each one. Our biggest torque is going to most likely have our biggest force overall. Biggest force is going to give us our biggest acceleration. And then we can convert that acceleration from this acceleration to our angular acceleration by dividing by r. So here we go. We know that D has got the biggest torque, so the biggest force. Our next one's going to be C, and then A, because it's 8, and then finally we have B, and that is number 19. If we go on, this is number 20. We have a 20 kilogram cafe sign, and it is being held up by both the wall here, so there's a little bit of normal force on the wall, but we more importantly have this string that's holding it up. And a wire is attached to prevent the sign from rotating. So they want us to find what is the tension in this wire. So we want to know what is the force of the tension. Okay, so let's go ahead and draw a different picture for this. So here's the pole itself. We know that we have this 3 kilogram sign hanging down here. We also know that this pole is 1 kilogram, and it is 1 kilogram right in the middle. So I'm going to draw a longer line. It doesn't represent the magnitude, it just shows you the position of where it's at. And these are both pulling down on the pole. So the pole's pulling itself down about this pivot point, and then this 3 kilogram the 3 kilogram sign is also pulling it down. So those are the two things making it go down and to the left. So it's actually trying to rotate this way. We want to find out what is the net torque on this thing. And so we've got to do the torques for each one of the objects that we have here. And that should be equal to the force on this wire. If we think about it, we want to have the force, okay, on the wire. We know that if we have the angle 30 degrees right here, we want to find out what is the force going up on the end of the wire. So this wire has two forces. It has a force that's going up, and it has a force to the left. We're more worried about this force. So that's actually this side of the triangle, so we can say that'd be the force of tension. So this side of the triangle would be force of tension times the sine of that 30 degrees. So let's use it first. This would be the tension force times the sine of 30 degrees. And notice that that tension force is acting over a total distance of 4 meters. So that would be torque number 1. So we can call it torque number 1. We also notice that this torque would be going up and to the left, so it would be pulling that rod up and to the left. So we'll draw a picture here. It would be drawing it this way, and we know that that is counterclockwise, so it's positive. So that's our first torque. Our second torque will be pulling it down to the left, and so because it's pulling it down to the left, this is clockwise, and so it's negative. So we're going to subtract off. Here we've got our force of 3 kilograms times, now force is mass times gravity, because it's the weight of the sign itself, so that would be 10, times, and now we're going to put in the distance it is from our pivot point, and that would be 3 meters. The last thing we have to subtract off is the actual rod itself. Notice it's also pulling it in a clockwise direction, so we're going to subtract 1 times 10, because that would be the weight. So that's mass times gravity. This one was mass times gravity times that radius. And then we are at the middle, we would be 2 meters away from the center. And so that's what our net torque should end up being. They want us, though, to find tension. So our net torques, when we add them up, should all be equal to 0. So here we'll put in T2, and this was T3. So this was torque 2, torque 2, and this was torque 3. So the two torques moving down should be equal to the torque number 1 moving up and to the left. So let's go ahead and put everything on the other side. So now we're going to end up with the tension. So the tension, we're going to solve for T, should be equal to, if we do our math, we'll end up with 54 newtons. And that would be the tension that we see, this FT line that we have right here. That would be the tension. For number 21, this is the next one. We have a 10 kilogram tortoise sits on a seesaw 1 meter from the fulcrum. Now the fulcrum is our balance point. It says, where must a 2 kilogram hair sit in order to maintain rotational equilibrium? So here's a picture of kind of what we have. We know that we have a 10 kilogram tortoise and we have a 2 kilogram hair. So I'm going to move this out this way. Usually these would be just kind of sitting out, so let's go ahead and make it here. The 10 kilogram tortoise sits 1 meter from the fulcrum, so we're going to go from here over to here, and this is 1 meter. And this is where our 10 kilogram tortoise would sit. Where would we have to put that hair in order for the hare or the rabbit to sit on this side to make sure that it's balanced? In order to do this one, then we know that we've got a rabbit, and the rabbit is over on this side, is 2 kilograms, but we're not sure about this distance, and so we're going to try to find it. So the sum of the torques, or the net torque here, should be equal to 0. We know that going in this direction, so this is counterclockwise, would be positive for the hare. So we're going to say, I'm sorry, positive for the tortoise. So that would be 10 kilograms times gravity times 1 meter. And that would be equal to the 2 kilograms of the rabbit times 10 meters per second squared for gravity times, we're not sure what that position it needs to be from the center, so that's what we're looking for. If you go through and you solve, and we solve for x, oops, yeah, we want to know how many meters. If we solve for that position, our position here should be, or radius should be 5, and that would be meters. So here's where the tortoise is. The hare would then need to be 5 meters out. So this is not to scale. It would look a lot different. It would probably look something more like this, where you would have the tortoise here, and then you would have the hare right really far out here. And that is number 21. We're going to stop there, and the next video will be on moment of inertia.